Hi everyone, welcome to today's session, Uncertainty in LLMs, where we will look at uncertainty quantification methods. We start with token and sequence probabilities, where the idea is that if we do have diffuse token probabilities, that they can reveal linguistic uncertainty. But the important caveat here is directly that the probability of a wording is not necessarily the probability of truth. Just because a certain word is predicted to have a very high probability to come next doesn't mean that it actually represents some true information. Measures that you can use for token and sequence probabilities is like our beloved entropy that we already looked at a lot. We can just look at the token probabilities itself or the gap between top candidates. These methods are very inexpensive because if you have access to those probabilities, which you only have in open models, you have access to the probabilities either way, and you can just, for example, put them into entropy calculation, which is like a very simple mathematical formula. And it was found that methods like that rank uncertainty very well on short constrained answers. So for example, the cat has lives. We can see that the number 9 has quite a high probability with 35% compared to the next ones. So, and here you can see how, for example, a distribution of token probabilities could look like. However, if we have very long answers or a lot of text, they also accumulate more negative log probability, because how LLMs work is that they do not always predict the very word that has the most probability, because oftentimes it might sound too robotic or create always the same outputs, and you want to have a little bit variation, so oftentimes it's sampled what comes next. And also we have the problem that many strings express the same meaning. So if you basically have words that have similar meaning or something, you can still have a high entropy because all those words receive some kind of probability mass, but they actually try to express the same thing. Also, common phrasing can make a false statement more probable. So just because the LLM saw that a lot in its training data, for example. And as I mentioned before, for methods like that, you really require access to those token probabilities, the internal layer outputs, or the LLM itself, which you not always have. Or actually you don't have it all when you use models like ChatGPT or Claude, for example. The next method we're going to look at is repeated sampling, where you basically just have a task prompt where you either just repeat the very same task prompt, and you need a model that has a so-called non-zero temperature. Temperature is basically a setting that tells you how diverse the opinions or the sentences should be, or how much it should really stick to just the very next probable word. And then you sample multiple answers, or another option would be to just vary the prompt a little and compare the answers. You can compare the lexical agreement, so basically just comparing the strings. But you can also do things like consistency scores, where you use the idea of entailment that we looked already in natural language inference at, where you kind of predict whether the various answers you get actually entail each other, so whether they say the same thing in a way. Important is that those divergent generations are a warning signal, but the agreement itself only shows sampling stability. And this has also some other limits, for example, that several samples multiply the inference cost. So especially if you're doing it large scale, it might be very problematic to actually, 3 times or 5 times increase your costs when prompting. Also, the results depend on the sampling settings. a model can repeat the same misconception, propaganda, or fabricated citation or whatever. So just because the sampling is stable doesn't mean that the output is really representing the truth. And it also does not verify any claim by itself. There is another method, semantic entropy, that's kind of similar. So you also generate multiple answers, but you don't just look at the token entropies, for example, but really the semantics. So semantics mean that certain term or certain sentences have the same meaning. And we can look at, for example, here examples. If you ask where is the Eiffel Tower and you get the answers Paris, it's Paris, or France's capital Paris, it basically all has the same meaning. But if you look at the tokens, it's just different things that the answer gives you. And if you just look here at the entropies of the answers, you see that there is a high entropy. But now, if you just cluster your answers, calculate one probability, wait, I'm moving a little so you can see the other bars as well. If you then calculate the probabilities on the clusters, you can see that here we actually have low semantic entropy. And the idea is that paraphrases should not count as disagreement, and this method was shown to work quite well to identify confabulations across question and answering, math, or biography generations. Also, again, the caveat here is that semantic instability or stability does not represent true sentences. It just says that the LLM is generating semantically similar meanings in its outputs. And the idea why you do that at all is basically the consistency hypothesis, which says that the generation consistency works as a proxy for the real confidence. So if you generate similar answers all the time, it's supposed to have a high confidence and a high accuracy then. But this is like a useful hypothesis, but this is not guaranteed in any way. So there can be wrong things generated a lot. But again, for simple question answering in math, for example, it worked very well. Okay. Then we have verbal confidence. So you can literally just ask your favorite LLM, give me a probability between 0 and 1 that this answer is true. Or you can just ask for low, medium, high confidence and add an explicit I do not know option. And interestingly enough, some studies find useful calibration in controlled settings, which means like they repeated certain experiments. So it does not necessarily mean that this also holds for all applications that you have in mind. But here, for example, you can see that verbalized probability has a better calibration, so it's closer to this line that we want to go back to the videos on the calibration if you don't remember well what those plots represent. But basically we want the bars to be very close to the diagonal, and it's a method that can already work. But again, this is generated language, so it can change with the exact phrasing that you ask for, with the examples, what kind of persona you're requesting, and in general with alignment methods that we will later look on even more. Another method is self-evaluation. So basically you prompt the LLM twice. First you ask for your answer, whatever you want to know, and then you give your question and the answer of the LLM, and then ask it again, is this proposed answer correct? And then you ask for example, or you don't ask is the answer correct or not, but you ask for the probability of it being correct. And you can see that if you compare the correct samples, which are the green ones here, with the incorrect samples, you can already see that here you can quite well differentiate between the incorrect ones and the correct ones. So obviously it's not perfect, so if you get a probability that the answer is true of 0.5, you can see that you have already quite some overlap between the green and the blue class, which is here this darker area. But again, if the probability is very, very high, you can see that that's mostly the correct samples, and if it's very, very low, that's mostly the incorrect samples. So you already see there is some differentiating, discriminating effect here. Problems are that the evaluator may share the generator's error. So the generator is the first LLM answer and the evaluator is the second one. So even, for example, if you use the very same model, this can already basically share the same error. But also if you have different ones, since oftentimes training data and so on is quite similar, the models may behave similar as well. However, it was shown that this can improve selective generation and abstention. So if you only let the model give you an answer if its expected self-evaluated probability of giving a true answer is high, it can actually improve that. We thank the Deutsche Forschungsgemeinschaft for funding this project. And this is our copyright, and goodbye everyone.